a little weird, but then it clicked, and I like this stuff.
Okay, all right. Yeah, so it's actually straightforward stuff.
Mm-hmm.
And we're just starting out. There are two sort of forms of the line. The first is the vector form, and the second is the parametric form. And if you followed through in the preamble, there was this thing we call the position vector. And it kind of takes us out to some point on what winds up being the line. And then there's a direction vector that just, it'll move us along that line to any place on the line we happen to want to go. And so I put a position vector to -2 and 3, and a direction vector of 1 and 2. Okay, and so the direction vector is the thing we multiply by some scalar, some parameter that generates the line. So hopefully the preamble kind of made that clear how that worked.
Yeah.
There are a couple of ways of writing this out. These actually add up, and because when you add vectors, you get a second vector. And so this awkward thing happens where you wind up with a resultant vector. So can you tell me
I think so.
What the vector equation is with this position vector and that direction vector?
Yeah, would it be -2, 3 plus s multiplied by 1, 2?
Exactly. So that is the vector equation of that line. And to get around this awkward thing where when they add together, they make this resultant vector, and the line is where the resultant vector tip is everywhere. They've sort of redone the notation, and they're saying L and then colon is equal to -2, 3 plus S times 1, 2.
Okay.
So that's just a way of getting around the whole issue that when you add them like that, you wind up with a vector.
Mm-hmm.
Okay. Now there's also the symmetric way of writing that line. And so
is that just breaking it down into the x and y components?
that's all it is. Yeah,
Yeah.
that's exactly what it is. It's just that simple. So for this line, what is the x given by?
-2 plus s, I guess. Just be 1s.
That's right. And y is just 3 plus 2s.
Yes, yeah.
And so all of sort of the questions revolve around trying to figure out, what is S, or what is the direction vector, or what is the position vector for the line?
Mm-hmm.
Okay, because we could pick a lot of different position vectors and wind up with the exact same line. That same line it can have multiple direction vectors, but those direction vectors are all going to be parallel. They're going to be some scalar combination of each other.
Mm-hmm.
Okay, I have a question for you. In fact,
right.
I kind of have 3 questions. So my first question, there we go. So vector, give the vector in parametric forms of a line through. So I picked 3 and 4 and 5 and 6. And so we just happen to have 2 points out here. Just goes to show that you should be a little bit more careful about how you choose your example points. So anyways, we're over here at 3 and 4, so there's a point there. And then we've gone over to 5 and 6, something like that. So here's 3 and 4, here's 5 and 6. And we want to come up with a vector equation that's going to go through those 2 points. Okay. And I'll just say this much. There are a lot of different vector equations that we could put in that would go through those 2 points. We're going to start out, pick a direction vector, sorry, pick a position vector that will definitely go through those 2 points or put us out there.
Would like 3, 4?
3, 4, right?
Work.
Yes, that would be my choice. Okay, there's our position vector. Good enough. How are we going to find our direction vector? It's probably as easy as you're thinking.
Would it just be like 5, 6, or there's something to do with it? Hold on. No.
Well, so we've got a position vector here. It's just 3, 4.
Yep.
Okay. Oh, this is I did a terrible job of drawing this. So here comes our direction vector. And we go over 2, and we go up 2. So our direction vector is just 2, 2. In other words...
So it's the slope of the next one. Okay.
Yeah, exactly. That's a great way to think about it. It's 5, 6 minus 3, 4. And so it's just 2, 2. And so we can actually give this equation as L1 is equal to 3, 4 plus S times 2, 2.
All right. Okay.
So, you know, we could have picked almost anything. We could have picked this for our position vector. We could have started at 5, 6 and chosen -2, -2 as a direction vector, or -1, -1 as a direction vector. So there are lots and lots of choices. And then if we wanted to get, if we wanted to produce the parametric version of that, it would just be 3 plus 2s and 4 plus 2s. And another way of expressing it would be 3 plus s or 4 plus s. So there's lots and lots of possibilities there for what the equation looks like.
Okay.
Okay. Does that seem straightforward?
Yep.
Perfect. Have another question. So this one, we're going to take it back to, we'll take it back to the good old y equals mx plus b form. Okay, give the equation of a line with a direction vector. Two, 3. And so I'm explicitly saying what the direction vector is. And it goes through 2 and 5. So we have a direction vector. Haha. Any good ideas for a position vector?
2, 5?
2, 5. Yes. And then this is our direction vector, and so it's definitely s times 2, 3. And if I wanted to turn this into the parametric form, it's 2 plus 2s. That's my x. And my y is 5 plus 3s. So I've got an expression for my x and for my y. So what's the y equals mx plus b form of this line? And so this is going to be one of those useful skills that we use a lot. And basically it involves expressing things in terms of the parameter s. And that winds up getting called the symmetric equation a little bit later on. And we use it in 3 dimensions as well as 2 dimensions. And so what I'm going to do is I'm actually going to express s in terms of x so that I can substitute it down into this equation. And when we're all done, we'll get it in y equals mx plus b form. So I know that x is equal to 2 plus 2s. And so x minus 2 is equal to 2s. And so s is equal to x minus 2 over 2. Okay, I've got a value for s here. And I have a value for s, or sorry, I have an equation that involves s over here. Parametric expression for the y variable. So I'm going to say y is equal to 5 plus 3 times x minus 2 over 2, because that was my s.
Right.
And now I'm just going to simplify until I get it into y equals mx plus b formation notation. Why don't I multiply everything by 2 to get rid of this stupid 2 down here that I thought I'd avoided? Oh, well. There, I'm multiplying everything through by 2. And now I'm going to expand the bracket. Tell me if I've made a mistake here, because I really thought I set this up so it wouldn't do this to me.
I think you're good so far.
2y is equal to 3x plus 4. Oh, I forgot the 2. And so y is equal to 3 halves x plus 2. So there. As long as I didn't make a mistake, which I won't rule out, we've converted that into y equals mx plus b form. And so, yeah, one of the things we'll wind up doing all the time is just switching back and forth from one form to the other. Okay. Sometimes one form gives us more information about the line than the other, or the information that we're interested in. Exactly. Okay, I think I have one more question, and then that's it. Okay, so here it comes. So we have two different expressions for a line. So here we are. So it's got a position vector 3, 4, and it has a direction vector of -3, -1. And we have a second line out here. So L2, and it has position vector 0, 1. In other words, it's just right up there on the up on the y-axis. Easy to figure out what the y-intercept is for that one. And so two different definitions for the line. The question is, are these two lines coincident? In other words, are they lying right on top of one another? Or are they parallel with each other, or do they intersect at a single point? Okay, so this is saying we've got a few different possibilities. They could look like this. They could be parallel. They could look like this. They could, have different slopes, and they could intersect. And the last possible option here is that they are actually the exact same line. Okay, because we can use different definitions and get exactly the same line.
So we just want to solve the y equals mx plus b form for both of them, or?
That is actually a really good, that's a really good suggestion. And it wasn't what I had in mind. But what you're saying is if we find the slope, and if we find what the y-intercept is, if those are the same, they're the same line. That is actually an excellent strategy. There's nothing wrong with it. In fact, I think it's probably just about as efficient as anything that I could choose. Yeah. Another way is to look and see, first of all, ask, are these two lines parallel with each other?
Mm-hmm.
Okay. And just looking at it, does it look to you like they're parallel, looking at the direction vectors?
I don't think so. Wait.
No?
Wait.
Okay. They actually are.
Yeah, they're multiples of 5. How do
yeah, so there's a way to tell.
Yeah.
And so if 6 and 2 is equal to some number, I don't know, let's call it n. So if 6 and 2 can be expressed as some scalar times -3 and 1, then they are, in fact, then they're parallel. So then the direction vectors are parallel.
I see.
Okay, so let's see if we can do this. So let's assume that they are. So 6 is equal to -3n. And so n is equal to negative 2. Okay, so for this to be true, n is equal to -2. So let's see if that gets us the second y value. And so 2 would have to be equal to n times -1. And so over here, we got a value of -2 for n. So -2 times -1 is equal to 2. So the answer is yes. The direction vectors are parallel. Okay. So just like you were saying, we could find the y equals mx plus b form of these lines. And if the slopes are the same and the y-intercepts are the same, then these are the same lines. Okay. We know know at least that they're parallel. We've established that one direction vector is a scalar multiple of the other. Now we have to see if they actually pass through the same point. Okay, so let's see if this line, line number 2, passes through 3 and 4. So that's the question we have to ask. So in other words, can we make 3 and 4 equal to 0 and 1? Plus t times 6 and 2. So 3 would have to be equal to 0 plus 6 times t for some value of t. And 4 would have to be equal to 1 plus 2t for some value of t. So let's find out what the value of t is here. So for number 1, 3 would have to be equal to 6t, so t would have to be equal to 1/2. So let's plug this into equation 2. Four would have to be equal to 1 plus 2 times 1/2. So 4 would have to be equal to 3. So the answer is no.
Yeah.
Okay. Those lines are parallel, sure enough, but they do not both go through the same point. So they are not coincident. They are parallel, but they're not coincident. These lines will never meet, which is sad, unless you get out to the end of the universe and it's a little different than we thought.
Exactly.
All right. Anyways, that's that. That's
pretty
vector and parametric equations, and it's pretty easy.
Yeah, that's good.
All right. So nothing tomorrow. I don't know. Maybe we can do a bit of review. Probably I'll give an overview of the test tomorrow. 5 questions, same as usual. Test on Friday.
Sounds good.
All right. Perfect. Then it's like 10 lessons left.
It's nice.
One Canada's Wonderland day.
Awesome.
All right.
Ready.
Good. Thanks, Jeff.
Yeah. Perfect. Thank you.